Hey, how you guys doing? Now we're in section 2.1 and we're going to look at some problems involving the derivative. I have your note sheet, and so I'm going to go over the examples and we're going to show you how to do some of these problems, okay? Alright, you ready? Here we go. Example 1. Alright. Example 1. Alright. Find the derivative. Find the derivative of f of x equal 2x minus 3 at the point 2, 1. Alright? So, bear in mind, when we say find the derivative, listen. We can very simply say find the slope. Okay? Find the derivative, that also means just find the slope. Alright? And if you remember, if you can recall from Algebra 1, that y equals mx plus b, which lets us know that the slope in this case is 2. So we know that our slope is 2. Okay, our derivative is 2. So we know the answer from Algebra 1, using Algebra 1, that the derivative is 2. However, we want to use calculus. We want to use calculus to show that the derivative is 2. So let's use calculus. Alright? And so, the limit as delta x gets very small of f of x plus delta x minus f of x, all divided by delta x. Alright, so this is our formula that we're going to use to find the derivative. Okay? And basically, ladies and gentlemen, all it is simply slope formula. That's all it is. It's a slope formula. So here we go. So we're going to take this portion right here. We're going to take this x plus delta x and substitute it in for x. Put x plus delta x in for x. Watch how we do that. So we're going to have the limit as delta x approaches 0 of 2 times x plus delta x minus, well, what is f of x? F of x is 2x minus 3. So it's going to be minus bracket 2x minus 3. All divided by delta x. If you make the correct substitutions, the problem is all algebraic, algebra 2 steps, and you're good. Okay? So now let's do all the algebra steps, and this is done. We're finished with it. Let's go. So we're going to have the limit as delta x gets very small. Take the 2 and distribute. We're going to have 2x, and then 2 times delta x, plus 2 delta x. Take the minus sign here and distribute. Minus 2x. Take the minus sign again and distribute. A negative times a negative just so happens to be a positive. Plus 3. Now, there is one thing that we did forget that's very, very important. Now, we have this 2 times x plus delta x, but I forgot to include the minus 3. So let me go back and pick that up. That's important. There should be a minus 3 right here. I got to pick up my minus 3. So that means I'm going to have to go back here and insert a minus 3. Minus 3. All right, now minus 2x plus 3. All divided by delta x. That's important. I left out that minus 3. That should be included in here as well. All right, so we got it. And so now let's see what cancels out. So the plus 2x's go to 0, and the minus 2x, that cancels. The plus 3 cancels the minus 3. And I'm going to be left with the limit as delta x approach 0 of 2 delta x divided by delta x. And as you can see, the delta x's will cancel out. Delta x cancels delta x, and the answer is 2. Which we said a long time ago. We said the derivative is 2. And that's the derivative in this case. It's 2. See? 2, 2. All right? Very good. Now let's do example 2. All right. Example number 2. All right. Let's see here. So now with example 2, we want to find the derivative of, let's see what it says here. Example 2. Okay. Find the derivative of f of x equals x squared plus 3. Find the derivative of f of x equals x squared plus 3 at the point -2, 7. At the point -2, 7. Okay, so again we're going at the derivative. Let's draw a picture. Let's sketch a picture very quickly of what's happening here. Let's look at the picture. So here we have a picture of our parabola. 1, 2, 3. It's a parabola that goes upward like this. All right. This is f of x equal x squared plus 3. Okay. Now at this point right here, this point, this is the point -2, 7. And right there at that point is a tangent line. There's a tangent line right here. And the tangent line touches the curve only at one point. And that's the point right there, -2, 7. So I want to know what is the slope of this curve at this point, which is the same thing as asking what is the slope of the tangent line at this point. Because this right here is called a tangent line. That's a tangent line. So what is the slope of the tangent line at this point? Or what is the slope of the curve, x squared plus 3, at this point? Let's go get it. Come on. Here we go. All right. Limit as delta x gets very small, approaches 0 or gets smaller. All right. F of x plus delta x minus f of x, all divided by delta x. Once again, you must take this x plus delta x and substitute it in for x right here. Put it in for x. Okay? So that's going to give us the limit as delta x gets smaller of x plus delta x quantity squared. See? X squared now is x plus delta x squared. This time, let's not forget, plus 3. Plus 3. Got it. Minus f of x. Minus bracket. Well, what is f of x? Oh, f of x is x squared plus 3. Minus x squared plus 3. All divided by delta x. Now we're good. We're good now. Now we're ready to do it. Alright? So now x plus delta x quantity squared, you have to FOIL that out. You have to FOIL it, okay? Let's work that through. So we have the limit as delta x approach 0 of x plus delta x times x plus delta x plus 3 minus x squared plus 3 all divided by delta x. So FOIL that out. Here we go. So we have the limit as delta x approach 0 of, that's going to give me, okay, x squared plus 2x delta x plus delta x quantity squared plus 3 minus, well, let's go ahead and take our negative sign and let's distribute it. All right? Minus x squared. And take the negative and go negative times 3. It's going to give me a negative 3. And it's all of this divided by delta x. What cancels out in the numerator? What goes? Let me see. Positive x squared, negative x squared. Positive 3, negative 3. Okay, we're on our way. Limit delta x gets very small of what? 2x delta x plus delta x quantity squared all divided by delta x. From my numerator, I can factor out a delta x. Take out a delta x. So I have the limit now as delta x gets very small. Take out a delta x. So I have delta x times 2x plus delta x all divided by delta x. And notice here, the delta x's cancel out. They go to 1. So this is going to equal 2x plus delta x. And as delta x gets very small, well, as it approaches 0, it gets smaller and smaller and smaller and smaller. So it's a very small number here. So now substitute in 0 for delta x. And that's going to equal 2x. All right, now, 2x is 2x now. This is the formula used to find the slope of the tangent line or the curve at the given point. You see, 2x is not the answer. It is not the answer. But it is the formula, you know, that we're going to use to find the slope of the tangent line, to find the slope of the curve at the point -2, 7. So in essence, what we have to do now is you take this x value right here, The x value is negative 2. You take negative 2 and you plug it in for x right there. And so that's going to give us 2 times negative 2, which is negative 4. Therefore, negative 4 is the slope or derivative of the tangent line or the curve at the point negative 2, 7. So again, we went through this entire process here to end up with 2x. 2x is the formula that we're going to use to find the slope of the tangent line, or to find the slope of this curve at the point negative 2, 7. And it's obvious, look, if the slope of the tangent line is negative 4, which makes sense. It's a negative slope. Why? Because this line is decreasing, see? It's going downward, it's decreasing. So it makes sense for the slope to be negative, because the line is decreasing, going down. Okay? You good? All right, if you don't understand anything I said, you can always like rewind the tape and go over it again and again and again. Or just see me in class. All right? Okay, that was example 2. Let's keep going. Let's erase. Let's erase. Let's erase. Let's erase. Let's erase. Let's erase. All right, example 3. Here we go. Example 3. Let's see what example 3 is here. Example number 3. All right. Our third example. All right. Find the derivative. Now we're going to use a different notation for derivative. The notation that we're going to use is f prime of x. This means derivative. Find the derivative. That's how you want to denote derivative now. F prime of x. Find the derivative of f of x equals the square root of x, and use the result to find the slope of the graph of f at 4, 2. So in general, it's just like the last problem. It's just like the last problem you got to finish doing. All right? All right, so we have the function. Let me sketch it very quickly. So we have the square root function. And somewhere out here is the point 4. And somewhere up here, I'm going to say it's right here, is 2. And there's a line that is tangent here. That only touches it at one location. There is a tangent line here with only one touch. Alright? There's a tangent line. This is my tangent line. And so I want to know what's the slope of the tangent line at this point. which is also like asking what's the slope of my curve at this point. Because the slope of the blue line, tangent line, is the same as the slope of the curve, the black curve, at this point. And this, of course, is the point 4, 2. Let's do the work. Here we go. Let's go get it. So we have, all right, the limit as delta x approaches 0, or gets smaller, of f of x plus delta x minus f of x all over delta x. So as we go after the derivative and determine what the derivative of this function is, we always start off with this function right here, with this expression rather. Use this expression to find the derivative. Limit delta x gets smaller, f of x plus delta x minus f of x divided by delta x. We always use this. All right? Here we go. So now we have the limit as delta x continues to get smaller, and you take this whole expression and put it in the radical. Radical x plus delta x, okay, minus what? F of x, which is radical x, divided by delta x, okay? Next step. Now, we have to recall a practice or a technique we learned for finding limits in our last chapter, which is called rationalization, because you have to rationalize in this case, because we have radicals here. So we have to rationalize. We have to multiply by 1. So in rationalizing our numerator, we multiply this fraction here by 1. So we're going to have to take this and multiply it now by the square root of x plus delta x plus, conjugate, plus radical x divided by the square root of x plus delta x plus radical x. All right? So now we have to multiply these two expressions together. Now let's multiply. And remember, our numerator is just like saying a plus b times a minus b, which equals a squared minus b squared. And so when I multiply them, here's what we're going to get. The limit as delta x gets very small. In my numerator, I'm going to have x plus delta x minus x divided by denominator. Do not combine anything in the denominator. Okay, don't multiply it through. So it's going to be delta x from here times the square root of x plus delta x plus the square root of x. And just leave it just like that. Okay? All right, let's simplify our numerators. What cancel in the numerator? Oh, I see. X minus x is 0. So now I'm going to have the limit as delta x gets very small of delta x divided by delta x times the square root of x plus delta x plus the square root of x. All right. Now what happens? Oh, look, we see cancellation. Delta x cancels and goes to 1. This delta x cancels and goes to 1 also. So now that's going to give us the limit as delta x approaches 0, or gets smaller rather, of 1 over the square root of x plus delta x plus the square root of x, which equals. Now at this point, you can go ahead and substitute directly. Substitute 0 in for delta x. So where delta x is, go ahead and put the 0 in for delta x right here. Put the 0 in there. And what are we going to get? We're going to get 1 over the square root of x plus the square root of x, which equal, and at this stage, with root x plus root x, you only add the coefficients. That's the one that's out front here and the one that's out front right there. So that's going to equal 1 divided by 2 square root of x. This is your formula now. That's the formula that you can use to find the slope of this tangent line. To find the slope of the tangent line at this point 4, 2. To find the slope of the curve at this point 4, 2. So now we take our x value. Our x value is 4. You take this 4 now and you put 4 in for x right here. Let's do that. So we're going to have 1 divided by 2 square root of 4, which equals 1 over 2 times 2, which equals 1/4. And 1/4, this is the slope of the tangent line. So the slope of this blue line is 4 at the point. At the point 4, 2. Okay? The slope of the curve f of x equals the square root of x is 4 at the point 4, 2. And there you go. That's what it's all about. So now, using tangent lines and derivatives, we can find the slope of a curve. Wow, calculus is wonderful. I mean, when we took Algebra 1, you could find the slope of a line, things that are straight. But now we're dealing with things that are curved. What's the slope of a curve? You know? In fact, in essence, it tells you how fast to take a curve when you're driving. If you're driving straight, you can, you're moving, you're going pretty at a good speed if you're going straight. Well, what if you're going around a curve? You can't go that fast. But you can determine your rate of change or the slope at a point on the curve and determine how fast you're going. But we're going to get into all that later, okay? That's coming. That's down the road. That's down the road. All right, so that's it for this example. Example 3 is done. All right, let's move on. This is over. Okay. All right. Okay, example 3 is done. What's the next one? All right. Find the derivative with respect to t. All right. Example 5. Example 5. All right. Y equals 2 divided by t. Find y prime. Find y prime. Y prime is another way of saying find the derivative of y. Okay? So this is like saying find the derivative of y, and I'll add this part in too, with respect to t. So we're going to find the derivative of y with respect to t. That's what this WRT means. with respect to. Make a note of that. WRT with respect to. So we're going to find the derivative of y with respect to t. All right, let's go get it. Here we go. So, limit. Let me use black. Black feels better on the whiteboard. All right, so we have limit as delta t now gets very small of f of delta t plus t. Well, it doesn't matter. It doesn't matter how you write it, okay? Let's turn it around. Let's write it as t plus delta t. It doesn't matter. Either way, of t plus delta t minus, in this case we're going to say f of t all over delta t. All right? And so, this part right here, t plus delta t, this goes in or substitutes in the place of t. And so what we're going to have, all right, so we have the limit as delta t gets very small of, plug it in, 2 divided by t plus delta t, see that? Minus f of t. Well, f of t is like saying y. F of t is 2 over t. All divided by delta t. Okay? So now we have to do the algebra on this somewhat complex fraction here. You know, we have a fraction, we're subtracting, finding the difference between two fractions, and it's all of that divided by delta t. So it's like a complex fraction we have going here, all right? So first, let's work in our numerator first, all right? Let's work in our numerator. Let's look at, if you will, let's consider 2 over t plus delta t minus 2 over t. Let's just deal with that one first, okay? Make that a little straighter. All right, let's deal with this one first. 2 over t plus delta t minus 2t, all right? Now remember our methods. When you're working or simplifying these fractions, remember you cross multiply, and then multiply going across the bottom in our denominators. Woo! See that? Cross multiply. Wah! And then multiply your denominators. Woo! Let's do it. So, you take the t times the 2. Here we go. And so we're going to have the limit as delta t continues to get smaller of 2t. And then you take the t plus delta t times the 2. All right? Minus 2 times t plus delta t divided by, and then you multiply our denominators going across the bottom. All right? T times t plus delta t. And this is all still over delta t. Okay, so far so good? You good? All right. Now, let's see if we can simplify our numerator. Let's do that, all right? We have the limit as delta t gets very small of 2t. Now take this minus 2 and distribute minus 2 times t. minus 2t, and then take your minus 2 times delta t, minus 2 delta t. All right, all divided by t times t plus delta t, all over delta t. What can we simplify in our numerator? Oh, 2t cancels 2t. All right, and so I'm going to have now the limit as delta t continues to get smaller of negative 2 delta t over t times t plus delta t, all divided by delta t. All right, now, next step. Now, this delta t here, I'm going to squeeze it right in here. Basically, I'm taking this and I'm really multiplying by its reciprocal. Okay? Or, you take this division line right here and this expression and bump it down and put this line on top of the bottom line. Just put the line right on top of it and this whole thing just boosts down one. So I'm going to have the limit as delta t gets very small of negative 2 delta t, all divided by t delta t times t plus delta t. You see? So this delta t squeezed right in between. There it is. And now it's kind of obvious what's going to happen here. It's kind of obvious that this delta t cancels this delta t. So I'm going to have the limit as delta t approaches 0 of negative 2 divided by t times t plus delta t. And now it's safe to go ahead and plug in 0 for delta t. It's safe to do that now. Go ahead. And if I do that, I'm going to have negative 2 over t times t plus 0, which equals negative 2 divided by, well, t times t is t squared, and that's it, folks. That's the derivative. Negative 2 divided by t squared is the derivative. And notice, I didn't want the derivative of this function at a particular point. Didn't ask for that. It just asked for the derivative. And here's the derivative. Which means if I were to give you a point, you could use the, like the x value of that point, plug it in, and you can find the slope of the curve at that given point. But they didn't ask for that. We didn't ask for that. All we wanted was the derivative. And there you have it. Negative 2 divided by t squared. Okay? All right. We're still in this section, this chapter, regarding derivatives. And we have to go forward because now we're going to look at continuity and differentiability. And so when you differentiate, or if a function is differentiable, it all, relates back to finding the derivative. Okay? So we want to look at differentiability being or having a derivative. That's differentiability, having a derivative, and continuity, and see how both of those two relate one to another. Okay? So let's do that. Differentiability and continuity. Okay, so now not every function is differentiable. What does that mean? This means have a derivative. That's all it means. Not every function have a derivative at certain points. Okay? Such functions have, here we go. What kind of functions have an issue with differentiability? What type of functions have an issue with having a derivative? Oh, functions such as this. 1. Sharp turns. 2. Vertical tangents. 3. Discontinuities. 4. Okay. Those 3 qualities or characteristics will render a function not differentiable at a point. Sharp turns, vertical tangent, discontinuities. They are all no good. Let's take a look at each 3. Let's take a look at each of them. All right? And to do that, you have to use we're going to use what we call the alternate form of the derivative. And the alternate form of the derivative is the limit as x approaches c of f of x minus f of c, f of x minus f of c divided by x minus c. This is the alternate form of the derivative that we're going to use in these cases. Cases in which the functions are not differentiable at a point. Cases where the function is not differentiable, having these characteristics: sharp turns, vertical tangents, discontinuities. In these 3 cases, for these 3 cases, we're going to use this alternative, or the alternate method, or the alternate form of finding a derivative. All right. So first, let's look at sharp turn. An example with a sharp turn. All right. So we're going to call this our sharp turn example. And what type of functions have sharp turns? Well, these are absolute value. Absolute value functions have a sharp turn. So let's say that f of x equals the absolute value of x minus 2. Show that f of x is continuous at x equals 2, but not differentiable at x equals 2. Okay? Well, here we go. Here's a sketch of the graph. All right. 1, 2. That's 2. And so our graph goes like this. That way. That way. That's a sketch. That's a sketch of our graph. All right. This is f of x equals the absolute value of x minus 2. As you can see, it's continuous. It's continuous because as we come at 2 from the left side and come at 2 from the right side, we get the same value, which is 0. All right? We plug in 2 for x. 2 minus 2 is 0. Absolute value of 0 is 0. So this is the point 2, 0. And we are defined right here at 2, 0. Okay? But now, let's look at our derivative. Let's look at our derivative using this right here as x approaches 2. All right? So let's look at the left side derivative. Here we go. The left side derivative, the limit as x approaches 2 from the left. If we use the left side derivative, we need f of x. We're going to use negative x minus 2 minus f of 2 over x minus 2. You see, with the absolute value, okay, we have to consider both sides, the negative side and the positive side. Okay? So if I'm coming from the left, you know, if I'm coming from the left, I'm coming from the negative side. That's why I have a negative right here. Because I'm coming at 2 from the left. So I'm coming this way. See that? That's negative. I'm coming in negative territory. Coming from the negative. So coming from the left side, I have the negative right here. So that's where I'm coming from. Alright? So this is going to equal negative x minus 2 minus, now put 2 in for x in our function. If I put 2 right here and I put 2 right here, 2 minus 2 is 0. After the value of 0 is 0. 0 over x minus 2. This equals the negative of x minus 2 over x minus 2, which is simply negative 1. So my left side derivative is negative 1. What about my right side derivative? Let's see. The limit. Okay, this is now the right side derivative. Right side derivative is right here. The limit as x approach 2, now from the right side. Now if I'm coming at 2 from the right side, I'm positive, coming from the positive side. Alright, so that's going to be x minus 2 minus f of 2 all over x minus 2, which equals x minus 2 minus, put 2 in for x again, you get 0 over x minus 2, which equals x minus 2 over x minus 2, which equals 1. And so my right derivative is 1. That renders the function not differentiable. You can have a derivative at this point different on each side. The derivative must be the same on both sides. So, this function is not differentiable. It's not differentiable at x equals 2. Because look, you at this point right here, at that point at 2, I have a tangent line coming here whose slope is negative 1. I have a tangent line coming here whose slope is positive 1. But listen, at any given point you can only have one line tangent now. You can't have 2 lines tangent same point. And if you do, it's not differentiable at the point. In fact, there are many tangent lines at that point. Watch this, look. Line tangent. Boom. Boom. Line tangent. See that? Man, I can keep going. Another line tangent. See? Another line tangent. All of them tangent lines at that one point. And so when you have a sharp turn, you leave this one point right here. That one point is prey for many tangent lines to be going through it. So, you know, it's not differentiable. Left side derivative and right side derivative are not the same. So this really kills differentiability, sharp turns. Okay, you good? You all right? Again, if you don't understand it, you can rewind the tape and go back over it again. All right, come on, let's go. That's sharp turns. Now let's look at vertical tangents. Sharp turns are done. Now let's go after the vertical tangents. Oh, I shouldn't have erased that. I need the alternate form, but it's okay. I'll put it back. All right. Let me put it back up here. The limit as x approach c of f of x minus f of c all over x minus c. All right, so now let's look at vertical tangents. Let's see the example in your packet for vertical tangents. All right. All right. Let's say the function f of x equals x to the power of 1/3, okay, is continuous at x equals 0. However, the limit is infinite. All right? Simply put, it's undefined. Let's see. All right, look. First off, let's graph it, do a sketch. X, Y. All right, now watch this. Here we go. Here's our graph. It looks something like this. Let me see. On this side, it's going to curl up like that. And on this side, it's going to curl down like that. There we go. That's not too bad. That's okay. That'll do. And this is f of x equals x to the power of 1/3. All right? And so now we're talking at x equals 0, right here. And so here we go. The limit as x approaches 0 of f of x, x to the 1/3, minus f of 0 all over x minus 0 equals x to the 1/3 minus, now put 0 in for x. You get 0 all divided by x, which equals x to the 1/3 divided by x, which equals, now, back to algebra 1 or algebra 2. What is x to the 1/3 divided by x? This is x to the power 1. What do you do with your exponents? What do you do with these two exponents? Very good. Subtract. So that's going to equal x to the 1/3 minus 1, which equals x to the negative 2/3. And this equals 1 over x to the 2/3. And so we have the limit as x approaches 0 of 1 over x to the 2/3, which equals infinity. That's infinity. Because as x gets very, very small, this here gets very, very large. As x gets small, this gets large. Someone's saying, Mr. Wright, I don't get that. I don't understand it. What do you mean? As x gets small, this gets large. Let me come at you like this. Watch this. Look. Look, come on. Come on over here. Watch this. All right. Let's say the limit as x gets very, very small of 1, let's just say over x for convenience. Now I'm telling you that this also equals infinity, just like this one does. But for convenience, I'm going to explain to you why this one. Okay, here we go. Pick a very small number. See, as x approaches 0, this means, what it means is as x gets very small. Give me a number that's very, very small. Oh, I got one for you. Look, how about 1 divided by 2 billion? That's a very small number, 1 divided by 2 billion. So we're going to let x be this number right here, 1 divided by 2 billion. So we have the limit as x gets very, very small of 1, here's the 1 on top, 1 over, oh, and what's our very small number? 1 over 2 billion. That's our very small number, 1 over 2 billion. Well, what does this equal? What is 1 divided by 1 over 2 billion? Yeah, you got it. 2 billion, man. That's 2 billion. So the point is this. As x gets very small, 1 over x gets very large. There you go. As x gets very small, 1 over 2 billion, then 1 over 1 over 2 billion is 2 billion. It gets very large. You clear on that? I hope so. All right. Good. So this goes to infinity. Okay? And so the only vertical tangent that we have at 0 is this vertical line right here. That's the only vertical tangent we have, is this line right here. All right? There's your tangent line, which is a vertical tangent line. And if you recall from Algebra 1, we said that the slope of a vertical line is undefined. Or is what? No slope. So this slope is undefined. Or what? No slope. Undefined. Because look, this is not a slope. A vertical line is not a slope. Imagine this. Watch this. Let's say you go skiing. You skiing now. You like to ski? Okay, well here you are. You standing right here. That's you. Alright, there you are. And you're about to ski right down this vertical line right here. Huh? That's not a slope, folks. That's a free fall. You out of here. That is no slope at all. That's just a flop. You're done. Alright? So this line here is truly no slope at all. That is a free fall. No slope. Undefined. Okay? And so vertical tangents also destroy differentiability. The last thing that destroys differentiability is discontinuities. Let's get it. Alright. Discontinuities. Why do I keep erasing the alternate form? I don't know why. Alright. Write it again. Alternate form of the derivative. Alright. Limit as x approaches c of f of x minus f of c all over x minus c. Okay. Now let's consider, now we want to show that f of x, which equals piecewise x squared plus 1 for x less than 0, and it's going to be negative x squared plus 4 for x greater than or equal to 0. All right. Let's show that this function is neither continuous, oh, I left out a u, all right, nor differentiable. At x equals 0. Okay, so let's first deal with the continuity of the matter. Let's see if it's continuous first. All right, so seeing if it's continuous, let's check for continuity. Well, before we check for continuity, let's graph it. Look at the graph. And then we do the algebra. Graph. X, Y. First, let's graph the first piece. I graph that in blue. X plus 1, go up 1. For x less than 0, that's going to be an open, so this is 1. Open circle at 1, and it goes upward like this. All right? Open circle at 1, and it goes upward. Okay? And that's 1 right there. And then negative x plus 4. So we go up 4, 1, 2, 3, 4. And at 4 we're going to have a closed circle. But this graph goes downward because it's negative. So it goes downward like this. So it's kind of obvious that it's not continuous. It's a jump discontinuity. So it's not continuous. That's kind of obvious. Can we show it's not continuous? Of course we can. Let's see. Let's go back to our rules of continuity. All right? So we're going to look at the limit as x approaches 0 from the left side, which is this function right here, which is x squared plus 1. Plug in 0, we get 1. And the limit as x approaches 0 from the right side, the bottom expression, which is negative x squared plus 4. Plug in 0, we get what? 4. And so the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right, so it's discontinuous at x equals 0. So we know it's discontinuous at x equals 0. Okay? Now let's show that it's not, or that's not differentiable. Let's show that it's not differentiable at x equals 0. Okay, we can do that. All right. Let's look at the limit as x approach 0 from the left side, and let's use our derivative formula, our alternate form of the derivative, because we're not talking about continuity now. Now we're determining whether it's differentiable from the left side. So we have to use our differentiable formula here. And let's look at it from the left side. So we have to take f of x. What's our left-sided formula? Or our left-side expression? Very good. Here's the left-sided expression right here. So f of x is x squared plus 1. All right? Minus f of 0 over x minus 0. The limit as x approaches 0 from the left side of x squared plus 1 minus. Folks, here's where you have to be careful, because this will get you if you're not careful. F of 0. This means plug 0 in for x. Plug 0 in for x. Both of these expressions cannot take 0. This expression right here, you can't use 0 in this expression, x squared plus 1, because x is strictly less than 0. So you can't use 0 right here into this expression. This expression, negative x squared plus 4, is x greater than or equal to. So you're going to have to plug 0 in for x in this one, because this one is less than or x equal to 0. So don't plug 0 in up here, because you're wrong. This one does not take 0. This one does. Come on. So, x squared plus 1 minus, all right, negative 0 squared plus 4, all divided by x. The limit as x gets or goes to the left of 0, what do we have here? X squared plus 1 minus 4 divided by x, which equals x squared minus 3 over x, which equals, now split it up, x squared over x minus 3 over x, all right, which is going to equal, now let's take this part, let's bring it over, let's keep working on it. That's going to give me the limit as x approaches 0 from the left side of x minus 3 over x. Question, if I plug in 0 now, this is going to give me 0 minus, where does 3 over x go? As x gets very small, what about 3 over x? What happens to that? That gets very what? You got it, large. So this goes into infinity. So this is going to give me infinity. And so therefore, it's infinity, so it's not differentiable. So coming in from the left side, right here, I'm coming in from the left. All right? As x approaches 0, as x gets close to 0, all right, I have an infinite limit here. Okay? So I have an infinite limit. And an infinite limit can come at you in several ways. An infinite limit can be 1, a vertical tangent line, or infinite limit can be 2, a missing point. An infinite limit can be either one. Because see, I don't have a vertical tangent here, but I do have a missing point. See that? That's also an infinite limit. All right? Whew. Deep breath. We're almost done. Hang in there. We're almost there. And the last point I want to make, this is going to wrap it up. Here's my last point. Last point. The last point is that differentiability implies continuity. Differentiability implies continuity. If a function is differentiable, then it is continuous at various points now. I'm talking about points here. If a function is differentiable at a point, then it's continuous at that point. All right? So if a function is differentiable at a point, then it's continuous at a point. All right? So let me write it out like this, because I'm going to use some geometry. Watch this. Here's what we're saying. Here's what we're saying, okay? If f is differentiable at x equals c, then f is continuous at x equals c. Let's go back to geometry. We have an if statement, an if-then statement. Okay? These are what we call conditional statements. And if you remember, or if you can recall, conditional statements use the arrow, like this. If then, right? So here's what we're saying. If a function at a point is differentiable, then it's continuous. So I can write it like this. If it's differentiable at a point, then it is continuous. DC. If it's differentiable, then it's continuous, right? And this is called the conditional statement. That's the conditional statement. Well, in geometry, if the conditional statement is true, then what else is true? Is it the inverse? Is it the converse? Or is it the contrapositive? If the conditional statement is true, what other statement is true? Is it the inverse? Is it the contrapositive? Is it the converse? Or is it all of them? Which one? Yeah, you're right. Yeah. If the conditional statement is true, then the contrapositive statement is also true. And so the contrapositive statement is, if a function is not continuous at x equals c, then it is not differentiable at x equals c. This is the contrapositive. And this is always true, both of them. Okay? So, if a function is differentiable, then it's continuous. True. If a function is not continuous, then it is not differentiable at these various points. Thanks for listening. Thanks for coming. And stay tuned for the next lesson. Good job, folks. Good job, guys. Bye-bye. See you.